Welcome to Beyond the Brackets. In today's lecture, we'll study Cauchy Euler equation, an equation of this form where ai's are constants and f of x is a function of x is called a Cauchy Euler equation. To solve this, we follow three steps. First, we put x is equal to e power t, then we solve the differential equation with respect to t, and we replace t by log x. Let's first identify the equation. If you observe, the coefficient of third order derivative is x cube, the second order derivative is x square, and the first order derivative is x. So the power of x matches the order of the derivative. So this is a Cauchy Euler equation. The first step is to put x is equal to e power t. The number of factors will be equal to the order of the derivative. For example, x cube into d cube by dx cube is a third order derivative. So we get three factors: d, d minus 1, d minus 2. For the second term, constant 3 is as it is. X square into d square by dx square is a second order derivative. So we get two factors, that is d and d minus 1. The third term, x into dy by dx, is first order derivative. So we write only one factor, that is t. And y is taken common for the entire equation is equal to x on the right hand side is written as e power t, and then log x will become t. Simplifying this, we get d cube plus 1 into y is equal to e power t plus t, which is the operator form. Its auxiliary equation is obtained by replacing d with m and equating it to 0. So we get m cube plus 1 is equal to 0. The roots of this equation are minus 1, 1 plus or minus I root 3 by 2. Here minus 1 is real and distinct root. For this, complementary function will be yc is equal to c1 e power minus t. 1 plus or minus I root 3 by 2 is a complex root where alpha is 1 by 2 and beta is root 3 by 2. For this, the complementary function will be e power t by 2 into c2 cos root 3 by 2t plus c3 sin root 3 by 2t. To find the particular integral, take the reciprocal of the operator form multiplied by the RHS. Here, the RHS contains e power t, which is type 1, and t, which is type 3. So, we'll solve both the terms separately. For type 1, where RHS is e power t, we use the substitution d is equal to a, where a is the coefficient of t, that is 1. So, substituting d is equal to 1, we get 1 by 1 plus 1 into e power t, which is e power t by 2. For the second term, which is of type 3, we try to take the constant common, but here the constant is already 1. So taking the whole term to the numerator, we get 1 plus d cube whole inverse. Expanding it with the formula 1 plus d inverse, which is 1 minus d plus d square minus d cube. Here d is equal to d cube. We observe that the right hand side has t, for which differentiation of t with respect to t will be 1. And all the higher order derivatives will be 0. Ignoring all the higher order derivatives, we are left with only 1. So 1 into t will be t. Solution is given by y is equal to yc plus yp. Substituting both the values, we get the solution of this problem. This solution is in terms of t. We have to replace t in terms of x. Since we have x is equal to e power t, so e power minus t will become 1 by x. E power t by 2 will become root x. c2 into root 3 by 2, t will become log x plus c3 into sine root 3 by 2. Again t will become log x plus e power t is x, so that becomes x by 2 plus t is again log x. Let's look into the second question. Again, our first step is to put x is equal to e power t. The first term, x square into d square by dx square, is a second order derivative. So we get two factors, d into d minus 1. Minus 3 is constant. The second term, x into dy by dx, is a first order derivative. So we get one factor, that is t. We take y common from all the terms is equal to RHS will be x square will be e power 2t and sine of log x will be sine t. Simplifying this, we get d square minus 4d plus 5 into y is equal to e power 2t into sine t. Its auxiliary equation is given by replacing d with m and equating it to 0. We get m square minus 4m plus 5 equal to 0. The roots of this equation are 2 plus or minus I, which are complex roots. Here alpha is 2 and beta is 1. The complementary function is given by e power 2t into c1 cos t plus c2 sin t. To find the particular integral, take the reciprocal of the operator form multiplied by the RHS. Here the RHS has e power 2t, that is type 1, in combination with sin t, that is type 2. So together it forms type 4. For type 4, we first solve for e power 2t by replacing d with d plus a, where a is the coefficient of t, that is 2. So we get 1 by d plus 2 whole square minus 4 into d plus 2 plus 5. D plus 2 whole square can be written as d square plus 4d plus 4, and the other term is minus 4d minus 8 plus 5. Simplifying this, we get d square plus 1. Solving for sin t, which is type 2, we replace d square with minus a square, where a is 1. So we get 1 by minus 1 plus 1, which becomes 0, that is a case of failure. Multiply the numerator by t and differentiate the denominator with respect to d. So t in the numerator and in the denominator, differentiation of d square will be 2d and differentiation of 1 will be 0. Since d is d by dx, so 1 by d will be integration. So integration of sin t will be minus cos t. Solution is given by y is equal to yc plus yp. Substitute the values, you get the solution in terms of t. Converting the solution in terms of x, since x is equal to e power t, so e power 2t will become x square. C1 into cos t will be written as cos of log x plus C2 into sin t will be written as sin of log x. Minus t is log x, e power 2t is x square divided by 2, cos t is cos of log x. Let's look into the last question. Here the first term x square into y double dash is a second order derivative. So we get two factors d into d minus 1 minus 3 x into y dash is a first order derivative. So we get one factor, that is d, plus 3, and we take y common for all the terms is equal to 0. Simplifying this further, we get the operator form d square minus 4d plus 3 into y is equal to 0. Its auxiliary equation is obtained by replacing d with m and equating it to 0. We get m square minus 4m plus 3 is equal to 0. The roots of this equation are 1 and 3, which are real and distinct. Complementary function is given by yc is equal to c1 e power t plus c2 e power 3t. Here the RHS is 0, so particular integral will be 0. So the solution in terms of t is c1 e power t plus c2 e power 3t. While converting it in terms of x, c1 into e power t will become x plus c2 into e power 3t will become x cube. Here the boundary conditions are given to find the values of the arbitrary constants c1 and c2. The first condition is y of 1 is equal to 0, which implies y is equal to 0 when x is equal to 1. Substituting these values in the equation, we get c1 plus c2 is equal to 0. Naming this as equation 1 before substituting the second boundary condition. Differentiation of y will be y dash is equal to c1, differentiation of x will be 1 plus c2, differentiation of x cube will be 3x square. Second boundary condition is y dash of 1 is equal to minus 2, that is y dash is equal to minus 2 when x is equal to 1. Substituting these values, we get c1 plus 3c2 is equal to minus 2. Solving equations 1 and 2, we get c1 as 1 and c2 as minus 1. Substituting both these values in equation A, we get the solution as y of x is equal to x minus x cube. Here, two more practice questions are included along with their solutions.